All right, Math 3, Unit 7, Lesson 4. Directions here say to write a new function based upon 3 modifications: a vertical shift up of 8, a horizontal shift left of 3, and then the vertical stretch or shrink. So we're going to take our function y equals x squared. Our vertical shift up of 8 is going to give us a plus 8 in this position. A shift left of 3 is going to give us an x plus 3 in that position, which may seem opposite because plus is to the right direction, but it's x minus that shift. And then a vertical stretch or shrink will give us a 4th right there. So what will happen is that our vertex will go to -3, 8, which I'm going to have to approximate it right about there. And then the 1/4 is going to widen our parabola out way more wide than the original x squared. All right, so the next one, we have our y equals 1 over. We get a shift up of 4, so put a plus 4 over here, and a horizontal shift to the right of 3, so that's going to be x minus a 3 right here. And then this says vertical stretch. To me, that's more of a flip over the axis, but that puts a negative sign in here. Okay, so the original graph is there, and we're going to go right 3 and up 4 to right about there. And our new asymptotes, which I'll do in red, will be here and here. So the original sort of center point for our asymptotes is the origin. Now it's the point 3, 4. And then what happens because of the negative sign is that this portion winds up being up, kind of like what you call the second quadrant. And the other portion here that was in the first kind of flips down. So I see that in my world, that's more of a flip than it is a stretch. All right, number 3, we've got our function y equal square root, and it says vertical shift none. So we're not going to have any plus anything afterwards unless you want to consider it plus 0. A shift to the left is going to give us an x plus 5. And then a vertical stretch or shrink 3, we're going to have a 3 here. So our graph, which is now located, sort of emanating from the origin, is going to shift back, way back here to -5, which is right there. And then this is somewhat of just a sketch. We're going to go stretched upward like that. So where, 1, you put in 1 into the square root of x, you'd get 1, which is this point. And if you go back here, that 1 is actually like -4, so this point would be a little bit higher. Okay, sine of x, y equals sine. Vertical shift up of 1 is going to give us a plus 1. Horizontal shift left of pi over 2, x plus pi over 2. And a vertical stretch of 3 is going to give us a 3 right there. So I guess this is our graph down here, so right, 4A and B. So we're going to shift back to pi over 2, which I guess is right there. And then our amplitude is going to be 3, so we're going to reach way up here to 4. And the period doesn't change, so it'll come up way down here to negative. Oops, we'll try that again. So we're right about here, so we're up, down, and up. So we went backwards and we stretched our graph. Okay, again, A little bit Desmos will hurt you here to verify. I would type in both just to verify what the things look like. Type in this into Desmos and type in the transformation, and you'll see it probably a little more clearly. All right, triangle ABC, AB is 1. Use the information to label the sides. 45, 45, 90. The ratio between the leg and the hypotenuse is root 2 to 1 or 1 to root 2. So in this case, the way I think about this is we're going from a long segment to a short. So this will be 1 divided by root 2, which is root 2 over 2. And this guy will be the same because it's isosceles. The next one says that we have an equilateral triangle and RS is 1. So equilateral triangle is RST. And this side right here, RS is 1. And a 30, 60, 90, the short leg, which in this case is R, is half the hypotenuse. This is our 30-degree angle. This is our 60. And the ratio between the short and long legs is root 3 to 1. We're going from short, BA, RA, to long, SA. I'm going to multiply by root 3, which is root 3 over 2. Okay, now on the chart here, it says use what you know about the unit circle and the information from the triangles up above. The sine of pi over 6 is going to be 1/2. The cosine is going to be root 3 over 2. And the tangent is the ratio between the sine and the cosine. So I'm putting 1/2 over root 3 over 2. The 2's cancel out. If you rationalize, you get root 3 over 3. The pi over 4, sine is root 2 over 2. Cosine is root 2 over 2. And the tangent is 1. For pi over 3, which is 60 degrees, remember this is 30 degrees, you can reference that triangle. This is 45 degrees, you can go up and reference the isosceles right triangle. And pi over 3 is 60 degrees, again go up and reference the 30, 60, 90. So this will be, the sine will be root 3 over 2, cosine will be 1/2, excuse me, and the tangent will be root 3. For pi over 2, we'll use our unit circle for this one. Pi over 2 is 0, 1. So the y value is 1. The x value is 0. And 1 over 0 is undefined. We don't get any tangent for that guy. Using the unit circle again for pi, the sine is going to be 0. This will be negative 1. The tangent will be 0. For 3 pi over 2, we're down at 0, negative 1. So negative 1 for the sine, 0 for the cosine, and undefined again because you can't divide by 0. And 2 pi is 0, 1, 0 because we're back on the unit circle again. This next section has us label the entire unit circle, so bear with me here. There's a little bit of, this is pi over 6, which is root 3 over 2, 1/2. Pi over 4, which is root 2 over 2, root 2 over 2. Pi over 3, notice this is the reverse of pi over 6. Up here we get pi over 2, this is 0, 1, which is pi over 2. Right, now we go into this quadrant, we're going to replicate the absolute values of these values in quadrant number 1. And moving along in terms of the radian measures, this is 2 pi over 3. This guy here is 3 pi over 4. And this guy is 5 pi over 6. The 2 pi over 3 is going to use the same coordinates as pi over 3, except it'll be negative 1/2 root 3 over 2. Same thing for pi over 4, it'll be negative root 2 over 2, root 2 over 2. And for 5 pi over 6, it'll be negative root 3 over 2, 1/2. This is pi, and that's negative 1, 0. All right, again, these next 3 points all reference back to quadrant number 1. And this is 7 pi over 6. This is 5 pi over 4. And this is 4 pi over 5. We'll get to that in a second. This is 4 pi over 3. So this guy will share the same values as pi over 6, except both negative. So negative root 3 over 2, negative 1/2 pi over 4, negative root 2 over 2, negative root 2 over 2. And down here, 4 pi over 3 will be negative 1/2, negative root 3 over 2. This is 3 pi over 2, which is 0, negative 1. Once again, these reference back, you look up these vertical lines, these reference back into quadrant 1. Quadrant 3 references back along sort of a diameter, and 2 to 1, you don't really see any lines, but this one references that way, if we did it. All right, so what's this going to be? This is going to share pi over 6. This is 11 pi over 6. 11 pi over 6. That. And that would be root 3 over 2, negative 1/2. We're in the positive negative quadrant. This is 7 pi over 4. Root 2 over 2, comma, negative root 2 over 2. And finally, this is where the 5 pi over 3 is. And that point is 1/2 negative root 3 over 2. Whew, very good. All right, fill in the chart for the tangent. The tangent at pi over 6 is root 3 over 3. The tangent at negative pi over 6 is going to be negative root 3 over 3. The tangent at pi over 3 is root 3. The tangent at negative pi over 3 is negative root 3. And the tangent of pi over 4 is 1. And the tangent of negative pi over 4 is negative 1. So these negatives are coming by rotation from here backwards. Here backwards. All right, so it says explain why these guys, why that table rather supports the fact that the tangent is odds. Keep in mind that an odd function, f at x versus f at the opposite of x, these two values have to be opposites of each other. And notice that pi over 3 and negative pi over 3 have opposite results. Negative pi over 6, negative pi over 6 goes over here, sorry. These have opposite results, and then pi over 4, negative pi over 4 have opposite results. So it looks like the tangent, at least in this table, as opposed to the tangent of the negative angle, they're not equal to each other, they're opposites. If they were equal, if f at x was equal to the f at negative x, then the function would be even. Even means symmetry in the y-axis, sort of like x squared. Odd means symmetry in the origin, sort of like x cubed is an odd function. All right, on we go. All right, so given ABC with angle C, a right angle, what's the measure of A plus B? That would be 90 degrees. So when you draw a right triangle, if 90 degrees are here, these other two spots have to be complementary and add up to 90. Identify the quadrants in which the sign is positive. That would be quadrants 1 and 2. So the sign is what? The y value. So this is positive, positive, negative, positive. Down here we get negative, negative, positive, negative. So the sign is positive here and here, which is quadrants 1 and 2. When is the cosine negative? Cosine is the x value. So if I go with some other great color like this, negative and negative for the cosine would mean quadrants 2 and 3. When is the tangent positive? Remember, the tangent is the ratio between the y value and the x value. And in quadrant 1, we get a positive to a positive, which is positive. And in quadrant 3, we get a negative divided by a negative. So this would be quadrants 1 and 3 for a tangent being positive. Why can't the cosine be greater than 1? If the definition here is that, not very unit circle. So when we draw a triangle into the unit circle, the radius of the unit circle is 1. So that means that the maximum value, and the cosine is the adjacent over the hypotenuse. And generally speaking, you would expect, in a right triangle, the adjacent side and the hypotenuse to be a proper fraction, right? The proper fraction means it's like, someplace in between -1 and 0, -1 and +1. The proper fractions lie in here, like a third, 2/5. Numerator smaller than denominator, basically. But in this case, the maximum value of the cosine is going to take place here at the point 0, 1, when that radius reaches out straight to that point. So it's really, bounded by 1, because the definition is the unit circle, or you could appeal to this right triangle. Name the angles of rotation when the sine and the cosine are equal. Okay, so in the first quadrant at pi/4, they're equal. So pi/4 plus any multiple of 2pi, we'll call it 2πn, where n is a counting number. And they're also equal in quadrant 3 at 3pi/4 is quadrant 2. They're also equal at 5pi/4 plus any multiple of 2pi. Now that n right there is an integer, so you could rotate backwards or forwards. So this one says, find for which trigonometric functions does a positive rotation and a negative rotation always give the same value. That would be the cosine function, because when you rotate, say, into quadrant number 1, that'll be a positive rotation. And then if you rotate the same number of degrees in reverse to quadrant number 4, down over here, notice that these two guys share the same x value. And if it were to be, rotate into quadrant, the initial rotation be into quadrant 2, over here, there we go. And then the negative rotation of equal magnitude to here, right there. Notice again, they share the same x value, which means it must be an even function, because f at x, the positive rotation, is always equal to the negative. Number 18, which I think, one more after this. Explain why in the unit circle the tangent is y/x. Okay, relatively simple explanation here. On the unit circle, we draw in our triangle. This is our angle of rotation. This is x and this is y, meaning this point up here is x comma y. And the tangent is defined as the opposite over the adjacent. So if I blow this up a little bit, the opposite of this angle of rotation is the y, and the adjacent is the x, which gives us that the tangent of an angle is the y over the x, which could also be argued is the sine of the angle over the cosine of the angle. And just looking ahead, the cotangent must be the x over the y, which is the cosine over the sine. Okay, now we have one more. Now explain why the sine of theta equals the cosine of 90 minus theta. So we're saying like the sine of 10 degrees is going to equal the cosine of 90 minus 10 degrees, which would mean the sine of 10 degrees is the same as the cosine of 80. Okay, well, why does this work? Well, if you look at a right triangle and you say maybe this is the 10 and this is the 80, and we put some letters on here, A, B, and C, the sine of 10 is the opposite, A, over the hypotenuse, C, and the cosine of 80 is the adjacent, which is also A, over C. So these two functions are called cofunctions. And whenever functions are cofunctions, the value of their complementary angles is always going to be equal. So even just to stretch ahead, the tangent of theta is going to equal the cotangent of 90 minus theta. Notice tangent, cotangent. The CO stands for complementary. So sine, cosine is complementary. So eventually we have cosecant theta. The same as the secant of 90 minus theta. Those are called the cofunctions. All right, so that wraps up that lesson. See you soon.